Alright, usually lecture 10 would start with a whole talk about the exam where I take questions and whatnot, and thus it's more appropriate to do that in Zoom, so I'm just going to go right into the material for this lecture. None of this is on exam 1, but that doesn't mean it doesn't relate to exam 1, because we're actually finishing acids and bases today with the diprotic acid titration, which ties in all these different ideas that you were learning before and that are definitely relevant for the test. Before we get into the titration though, we do have one video to watch about this concept called predominant species, and before I even get into that, let's just do a quick recap. In the last lecture, we learned about diprotic acids in their various forms: fully protonated, 2 protons to lose, no protons to gain; fully deprotonated, 2 protons lost, they can only gain protons; and then the intermediate in between, which could either lose a proton or gain a proton. And sometimes these species might have different charges. Some diprotic acids are neutral when both protons are present. Some, like the one we used in our example last lecture, leucine, have a single plus charge when both protons are present, and some have a +2 charge when both protons are present, in which case their fully deprotonated base form is neutral. But regardless of the charge or how we're writing out the formula, if it's got 2 protons, we calculate the pH the same way, which is we just pretend like there's only 1 proton to lose and solve for the H+ concentration and pH the way we would back when it actually was a monoprotic acid. By learning the concentration of H+ that's formed from that first proton being lost, we also learn the concentration of the intermediate form that's left over. And some tiny portion of that intermediate can then form some of this basic form by losing the second proton. And to figure out that concentration, we just set it equal to the second Ka value. Notice we dropped the A subscript. In polyprotic acids, we can drop the A subscript. We just always have to keep the B subscript so that we have some kind of specification of what's what. And so basic form, on that note, works very much the same as the acidic form. We pretend that only the first proton acquisition matters. We treat it as a monoprotic base, and thus calculate the hydroxide concentration that we get from that first base reaction. And from there we can get the pH. We use a similar approximation. The concentration of the acidic form that's ultimately produced is just going to be equal to the second Kb value. It's the intermediate form that works differently from anything we'd seen. If we started with the intermediate form of an acid, for example, if we had a bottle of HL and we dumped it in some water and let it dissociate and associate, since it can lose protons and gain them, what does its final pH wind up being after equilibrium is reached? Well, it winds up being rather simple to calculate.
We just add the 2 pKa values together
and then divide by 2. To calculate the basic or acidic form that's produced by these reactions, you actually have to do some math, which we went over last lecture. However, once you've calculated one, you've calculated the other because these two are going to be equal. And all of these points are going to be important as we go through the diprotic titration later. We also spent quite a bit of time discussing indicators, and indicators are just an acid conjugate base pair that happen to have different colors from each other. And so the idea is that when one of these becomes more dominant than the other, the color of the solution changes. And we want that color change to happen at the equivalence point. And the key to all of that working is this relationship here that I had you write down, but I didn't explain it at the time, like why this works. And that's actually what we're going to start discussing in this lecture. That when the pH is lower than the pKa, then the acid form dominates. But when the pH is greater than the pKa, then it's the base form that dominates. So let's see where I'm coming up with these relationships from. So we're going to make some notes and call this section predominant species. Predominant species at a given pH. So an example of what I mean by this is, let's say we have a solution that is at pH equals 7. And let's say this solution contained acetic acid and its conjugate base acetate ion. What I'm going to now ask is, which is the principal form? So principal form of acetic acid, equals question mark. So in this scenario, imagine what happened was we had a flask of acetic acid, but then we titrate it with some strong base and eventually reach the pH of 7. So what do I have more of at this point, acetic acid or the acetate ion? So to figure this out, we're going to use the Henderson-Hasselbalch equation. First, let's just look at the species we're dealing with. We've got acetic acid, HC2H3O2. We know there is some equilibrium that exists between it and its conjugate base, C2H3O2 minus, and of course a proton, all in water. And now I'm going to use the Henderson-Hasselbalch equation to see which of these species dominates at this particular pH. I know on the left side of my equation is 7, our pH in other words. I know it's going to be equal to the pKa, which for acetic acid we can look up and find that is 4.76. And then we know we add the log of the ratio of our conjugate base, I'll just use the abbreviation A minus, to the acid, HA. And now what I'm going to solve for is that ratio of A minus to HA. So simple algebra, I would subtract 4.76 from both sides, and then I would get rid of that log. If I do that right, I will end up with 10 to the 2.24 is equal to the ratio of concentrations of acetate ion to acetic acid, but what I'm doing could work for any acid-base conjugate pair. And then if I plug that into my calculator and solve, I will get 170. Now, with a ratio equal to 170, quickly pause the video and ask yourself, is the Henderson-Hasselbalch reliable in this situation? So the answer is not really. And the hidden question that I just asked is this an effective buffer solution? Because we're only supposed to use the Henderson-Hasselbalch equation when you have an effective buffer. Otherwise, it's not nearly as accurate for calculating the pH. So 170, that might not be quite right for that ratio, but what is definitely true is that we have more A minus than HA. It's A minus dominant. Maybe it's not actually exactly 170 times greater than the HA, that part might be unreliable, but the part where we have way more A minus than HA, that is not in question. The conjugate base, the acetate ion, is dominant in this solution when we're at a pH of 7. And so the bottom line is, the Henderson-Hasselbalch equation can be used to quickly show that if the pH is greater than the pKa, like it is in this example, then that means that the conjugate base form is dominant in solution. Conversely, if the pH is less than the pKa, you can use the Henderson-Hasselbalch equation to prove that HA will be the dominant form. And of course, if the pH is equal to the pKa, you should already know where this is going. Neither is dominant. HA equals A minus. They have the same concentration, and this is not the first time we've stressed the idea that when these two are equal, the pH and pKa are also equal. And so this is the logic of an indicator. The indicator has its own pKa value, and as you titrate a solution and cause the pH to either go up or down, we start to change which species is dominant, and because they have different colors, the color of the solution changes as well.